Hi, thanks for having me here today. My name is Tony Rippy. I'm an engineer at Google, and I'm part of a team at Google called Production Monitoring SRE. And what we do is run monitoring systems at Google in their production data centers. We do all sorts of things along data collection, storage, serving queries, dashboards, alerting, the whole kit and caboodle. We're a distributed team. We have half of our team in New York City and the other half in Zurich, Switzerland. We do this for on-call response. We have a follow-the-sun rotation, so we can provide 24/7 support for our services. But we're not alone in this. There are actually many teams at Google that work on monitoring systems and contribute to various areas of monitoring, all the way from the West Coast, East Coast, Europe, and Australia. So what does this talk about? I'm going to be talking about monitoring systems. In particular, I'm going to try and cover the story of how the in-house monitoring system came to be at Google. It mostly focuses on white box monitoring just to kind of keep the scope small. And in particular, I want to talk about some of the systems that worked and a lot of the systems that didn't and why they didn't work. And my hope is that by talking about this and kind of opening up about it and sharing our experiences, that you guys will find this valuable and will kind of help move monitoring forward. Some disclaimers before I start. I didn't write this stuff. I joined Google back in 2009. This actually represents the work of hundreds of engineers over the life of the company. Also, I'm going to be going very fast over some of these technologies. There's not a lot of time, so I don't go too deep. But I'm going to be watching the Slack channel after the talk. If you have questions there, please post them and I'll be responding and trying to give some more information. So, let's start our journey back in 1999. At this point, Google is really young. This is less than a year after they were incorporated. They're excited, they're a startup, they're writing lots of code, and all the engineers know machines by name. If you've ever heard the pets versus cattle analogy, machines at this time are very much well-loved pets. And this was the Google homepage back then, if you've ever seen it, and back in 1999, very old school. But the main question on the mind of the engineers is, right now, is the website up and running? And how would you answer that question? And answering that question resulted in the first lines of monitoring code written at Google in all of their glory. It was a system called MonGoogle. It was a Perl script that somebody was running on their desktop. It would open up a connection to the Google homepage, try an HTTP GET, and if it worked, great, log it and continue. But if it didn't work, well, now wait a minute, it's running on my desktop. Is Google actually down, or is just the network in the office broken? Well, ping Yahoo. If Yahoo's up, then obviously the website must be down, and you've got to do something about it. Tell an on-call engineer. So these are very humble beginnings, but it didn't stay this simple for very long. These sorts of online checks were very useful. More checks were added to different endpoints, different websites, and they did other things. But mostly it was checks that went out, did something in production, got data back, examined the data, and if it detected something was wrong, to notify a human being. As it went on, more people started contributing to checks, and more things started adding to the system. And it eventually grew to the point where it needed to be converted from Perl to Python, and eventually from Python to a set of libraries, because it grew to over 3,000 lines of code. I don't want to dwell too much on it, but I want to talk about some of the reasons that it was successful that I think are important. First of all, it was simple. It was easy to reason about. It did one thing, and it did one thing well. And it also had very few dependencies, which means that this monitoring system can be deployed in all kinds of environments. All you needed was a Python runtime, and you could do whatever you needed to do. Some things that didn't work too well, obviously there were rewrites along the way, as I had mentioned. Some of the reasons, it's useful to look at why those rewrites happened. And giving reference to some of the talks from yesterday, one of the reasons the rewrite happened was testability. This system was one giant config file that contained a bunch of checks. And so it was totally possible that you could add a check that broke other people's monitoring. So testing was very important. And so when breaking it up into libraries, they made sure it was mockable, they could do replay data, and you had some good confidence in the changes you were making was actually that monitoring would continue to work. And also graceful recovery from failure. At the time, this system was very much stateless. So if it just sent an alert, and then the system crashed or something rebooted, it would check that the problem was still going, and then page you again. And if it started flapping, it would page you again and again and again and again. And this wasn't great. So this prompted people to start writing state to disk. and to be able to have graceful recovery from failure. So this wasn't our only monitoring at Google, of course. We'd actually used a bunch of open source software that was available at the time back in the 90s. Some of you may have used some of these systems in the past. We also had external providers checking the Google homepage just to give us a view of whether the website was up from outside Google's point of view. We still do that today as far as I know. But we can't talk about monitoring at a web company without talking about logs. HTTP logs are a source of a lot of the business critical metrics for any kind of a website. It contains things like click-through rates and active users, and logs are very much the source of truth. And we had some software that was effectively a Python script that goes through and read logs line by line, generating metrics and then storing them into a database. We used those to alert on in very simple threshold-based ways at the time. But it had a problem, right? With any log processing system, there's a delay. And at the time where you're the most busiest, when you most want to know what's going on, that's when the delay grows and grows and grows. And this wasn't great for on-call response. So some effort was put into a system called RGM. And this was to provide real-time telemetry on what was happening right now with the Google web page. It had gaps with the server monitoring, and that Google couldn't really help you in these cases, because those are simple, just go out and check something. And sometimes problems can be hidden behind caching and load balancing. So the way that worked, obviously, was monitoring web servers. So it made sense at the time to put up a special monitoring endpoint. And you would make an HTTP request against this, and it would dump a giant state vector out to just a text output. It's a simple, straightforward list of numbers, monotonically increasing counters, and there was no p-value pairs, there was no indexes. You just had to know that the third item on the list was the number of requests coming from Netscape browsers, and it was crazy. It was tough to change, and systems around it were very brittle. We used the same sort of idea for other things, for system and host level monitoring. We had a system called SVS, which was a system variable server, and it would gather certain metrics about the system. But it also had an interesting property. It had a local port that allowed other software running on the machine to be able to accept streaming data into it. So your job could start up and run on the machine, talk to a well-known port on the local host, and say, here are some variables, some internal state variables that I have that I want you to hold on my behalf. And the SVS daemon was able to hold all of that in memory and make it available. And this is used mostly for diagnostics. The SVS daemon had a built-in REPL where you could log in, tell it into a port, and issue commands and inspect variables on the fly about all aspects of what was running on that machine. This wasn't hooked up to any actual monitoring. At this time, it was just diagnostic and looking for what the current state of things are. Now, obviously, as Google got more machines and they started to scale out, logging into each machine and looking at the state of the machine doesn't make sense. It doesn't scale. So very soon, somebody came up with the idea of this system called the concentrator. And it had the same interface as SVS. You could still log into it and issue the same queries. But what it would do in this case is when you're asking for a particular variable, it would go out to a set of machines and in parallel run that same request on those machines, gather the results, aggregate them, and give you those results. But again, it's still limited. It's not hooked up to any monitoring system. There's no alerting with this. It's still for diagnostics. As you can see at this point, we have a lot of different tools and a lot of bits and pieces, but we don't have anything that you could call a modern or cohesive monitoring system. So fast forward a little bit to 2001. This is a big time within the company. So it was after the dot-com bust, but even despite that, websites, the number of websites were growing exponentially. And this was a big challenge to our web crawling team because they're struggling trying to figure out how we're going to deal with this explosion of data. And so at this time, there was a lot of innovation happening in-house with our infrastructure, trying to figure out how we're going to scale. Some notable developments around this time are GFS, the distributed file system. And this hit monitoring as well. How are we going to monitor these big services, distributed services we're building to handle the web crawling problem? And so they took some of the pieces that were around and they built this thing called CMON, the crawl monitor. And this used the concentrator that before was just a dumb ad hoc query type of tool, and they added polling to it. It had to go out and grab on a periodic basis all the metrics, a complete metric dump from all the servers in our data center. And would gather that in one place. It would store it locally in RRD files. It made it available for graphing and dashboards. And this was a big step forward at the time. This is approaching more of what we had as a monitoring system. Once it had all this data, it was able to run a set of alerting rules on it. The same sort of thing, basic thresholds. They did do some interesting things with thresholds, like some of the thresholds they set for how long the entire web scraping job are we. They had different thresholds for different escalation levels. If some error rate got to this high, call an on-call engineer. If it got this high, then oh my God, call Larry Page. They had that kind of escalation in place at the time. Some of the lessons here is that, having flexible alerting was a huge win, and it made the system usable. Some of the things weren't very good. So first of all, this was kind of hacked up at the time. And in fact, the config file was this giant Python config. It was a set of tuples that got loaded and evaluated at runtime, which is terrible for all sorts of reasons. And in particular, this monitoring system was very much set for the crawl pipeline. In fact, it had hard-coded values of different types of servers that were part of the pipeline at the time. And it had a much worse problem, which is for the on-call responders. All the rule evaluation is done by these concentrators, which there might be a concentrator for this set of machines over here that's getting data, and it detects a problem and fires an alert. Then there's machines over here, and it detects a problem and fires an alert, but quite often they're the same problem, they're just hitting a different set of machines. And this was terrible because you would get pager storms for one root cause, but you would have all these concentrators blowing up and sending alerts all over the place. And the thought was, we can do better. And they tried to do better with a system called GEMS, with a very grandiose title, the Google Expert Monitoring System, but it really wasn't. What this did is it took the concept of CMON and the concentrator in the same way it was doing data collection and added an additional layer. Rather than having the concentrator sending alerts in isolation, it packaged up and sent that data to a central place, something they called the collector, so that not only was data being aggregated to a central repository, but the alerts that were firing were being brought to a data repository. And it allowed you to do alerting rules on alerts themselves, kind of a very meta level thing. And the point behind this was to be able to detect, hey, I see these 60 alerts firing all over the place, but they all seem to be coming from the same system or have the same root cause, so I will send one alert to the on-call engineer. And the whole point of this was to reduce spam. It was very complicated. It had lots of moving pieces, which is not great in a modern system together. And it had one really critical problem. This was hacked up for the most part, and all of these were single points of failure, and they had all kinds of reliability problems. So this was terrible, and they actually spent a lot of time trying to fix this. There was a rewrite, and they made everything redundant. They went through and made sure there was redundant servers, that everything was being done in parallel. There were databases, and it was replicated, and it was fantastic. A hot failover. You could shoot any part in the head, and it would keep going. But they didn't focus on the usability of the system. The thing that ended up killing it was nothing to do with this sort of thing and this sort of like systems engineering. The problem that killed it was twofold. One, the simple explanation was that the config file was terrible. They took the idea of these giant sets of tuples from CMON, and they made it even worse. Because now, not only do you have the alerts that were coming in about data, but now you had another level on that where you're trying to configure how you should set alerts on the alerts themselves. And it was very unwieldy. According to one engineer that I talked to, there was only about 3 people at the company that really understood what was going on. And the effect of that was that you set the alerts once, you just got it running, and you never touched it again. And this is deadly, because then you're not tuning your alerts. When they're spammy, you don't adjust thresholds, and that means that the alerts that it was sending, even though there were less alerts, it was getting more and more spammy over time. And people just started ignoring there's too much noise. It had another problem in that the concentrators were still aggregating data and running alert rules on the data for just the scope that it had. And there's a subtle problem there. And the problem is that the alert rules could only operate on the data that it had. And so your collection hierarchy actually dictated the things that you could alert on. And this came to the forefront in this time period because we started getting these hot new Opteron machines that had very different performance characteristics than other machines in the fleet. And what you wanted to do was set different thresholds for machines that had better performance characteristics or different architectures. And this system didn't allow you to do that. You could only operate on the summary of data of the machines that you saw from the way the monitoring was collected in the system. And that's terrible. So they wanted to fix those problems, and so they were working on a rewrite of GEMS 3, but in the meantime, something bigger happened. This is around 2004. This is a big year for Google, kind of an earthquake in way of things. Because Google went public, they were flush with cash, and they're growing like crazy. They're scaling everything up. The SRE organization was formed, and there was a lot of thought within the company for how do we do operations at Google. And in particular, we introduced a system that fundamentally changed the way how we manage things, and that was Borg. I don't know if any people are familiar with this, but it is our job scheduler within Google. There's now an open source paper, or an open paper about this. I got a link out here, I can put it in the chat channel. And if you've ever used Apache Mesos, it's kind of like Apache Mesos in the same way. And this changed a whole lot of things. Like up to this point, people were managed machines. I run my software on my machine. And there's a well-known port and address. And now in this new world, you specified how you wanted things to run, but you couldn't specify where it was going to run or when. Things would get moved around on you. First it was over here, then all of a sudden that same job is now over here because it got preempted or there was a machine failure. Sometimes you got dynamic ports, and you even know what port to listen to in some cases. How on earth do you monitor jobs in this world? And it turns out that they put a lot of thought into this, into the original design of Borg. And they wanted to use a combination of white box and black box monitoring. Black box, just simple checks to go out and see is the service up and responding. And white box to be able to collect telemetry and add support for that within the system itself. The original idea is that you would bundle all your jobs in a service construct, and that the Borg scheduler would start up a mon-Google instance to do the health checks and start up your own private GEMS concentrator to be able to collect this data. But they didn't end up going that route because they started rethinking things. And if you look at it, if you squint, monitoring jobs are just another job that you want to run in the system, plus people wanted to be able to tune their monitoring in certain ways. And the result was this system called BorgMon. BorgMon was a very different beast. It was a rewrite of anything. They borrowed concepts from what came before, but it was a rewrite in C++. It was high performance, very multi-threaded, and it was composable. They broke the problem of monitoring into separate infrastructures. There was a separate white box infrastructure, black box, alerting, time series storage. All these problems were separate systems that interacted in a loosely coupled manner. And you could set up a monitoring system that was appropriate for your service and how it was distributed in Google's data centers. And that was very valuable and flexible and allowed it to be used in all sorts of situations. Rather than having giant Python configs, which was the state of the art to date, this one had domain-specific languages for being able to express monitoring in ways and using monitoring concepts. And that was a big change at the time. So this is how it worked. If you were a service owner, you had your processes that were running in Borg, and you ran this BorgMon job just as another job, but somewhere nearby your other tasks so that you could reach out and collect it. The BorgMon instance would discover your tasks. It would talk to Borg. It had something called the Borg naming service. It would detect where your tasks are running by IP and port, and then go out and collect data from it. And we had a client library that was like RGM, HTTP based. It would send an HTTP request to a well-known port, which would give a dump of all internal state variables and then hold on to that to you, very much like RGM and the concentrator. So it's holding this data in memory, and you would periodically checkpoint this, all of its memory state to disk. And the advantage here is that if the BorgMon ever died or was rescheduled or restarted, you can come back up and your data loss would be minimal. It can pick up from where it left off. And you would only be missing data for that time period for how long it took the service to restart. It only stored the most recent data in memory, and then when data started going outside the time horizon, you could write it out to log files on disk so you could use that for later analysis. They were composable, just like the concentrator. The BorgMon exposed the same interface as it consumed. So you could have something where you have local BorgMons looking at your jobs, and then have a global one that can talk to all the other BorgMons in different data centers and get an aggregate view of the performance of your application in one central place. And it had alerting rules. It could look over these sets of data, and if it detected that something was anomalous, it could send an RPC, rather than sending an email itself or trying to respond to it right there, it sent an RPC to a separate service called Borg Alert. And this is the entry point for an entire alerting infrastructure. So the data model. So we tried to learn from the past with this one, rather than just having variables and having incredibly kludgy variable names. They invented the concept of a label set. It was key value pairs that uniquely identified a time series. And these label sets would be travel through the system and through the storage and be retained along the way, so that even once aggregated into a central place, you could slice and dice the data in meaningful ways. I'm not going to go too much into this, because at this point this might be appearing quite familiar to people in the audience here. And that's because this is very similar to Prometheus. Prometheus is an open source monitoring system that was actually written by ex-Googlers that left and went to SoundCloud. And there's a lot of similarities there in how they handle it and their data model. I have a coworker here, Jamie Wilkinson, that is going to be giving a talk tomorrow on Prometheus. And if you're interested in this, I would highly recommend going to that talk and learning more about it there. One common theme here is configuration, and while Borgmon made it better, it wasn't perfect. It had these domain-specific languages all over the place. They had one query language, they had another one for doing alerting rules, they had a way of doing derived data, and you had to know a HTML template language for doing dashboards. So it added up after a while. There was a lot of configuration involved. I briefly mentioned Borg Alert. I'm not going to talk too much about this in the interest of time, but it is a very highly reliable infrastructure at Google. And there's some interesting decisions made there, design decisions on how to keep this up and running. Because this system needed to be available when everything else was burning. So there's all sorts of layers of fallbacks, and there's redundancy. And some of the interesting choices we made along the way is that when things start failing, we would rather overpage than underpage. So we made decisions along the lines of when doing master election, if there's a net split, we had a particular master election technique that made sure that we had a master on both sides of the split, so that you can be continuing to send alerts even when things were breaking within the network. Also, I mentioned that we could do historical time analysis. Borgmon did not talk to any external system, it just dumped raw files to disk. Well, we had a system called TSDB that went around and read all these log files and it copied them to a central location. Now the files that are getting dumped out are just raw time series data, it's not efficient for lookups. So it had two parts. The first one is this thing called the TS indexer, which read in all this data and then changed it into a different file format. It stored it in indexed files in disk that made it in a format that was efficient for lookups. And we also had this service called the TS lookup that would read these index files. It would respond to queries along the lines, give me this variable for this time period at this sampling rate with these label sets, and aggregate it together for me. And it would take these queries, read all the various index files, consolidate the information, and send it back. Now, users, when they wanted to see their dashboards or run queries, would go to their local Borgmon console, and it was smart enough to know whether the data you're looking for was in memory, or whether part of it was in memory and part of it was in long-term storage. And so it, behind the scenes, would go out and talk to the TSDB to be able to look up the information, piece it together, and then show the data to you in one result. So how do you know whether your Borgmon is still running or not? At this point, these systems are really starting to depend on a lot of infrastructure, and dependencies are a problem in monitoring systems. I mean, if we go back and look at TSDB, these big blobs are a distributed file system, it's GFS. All those jobs are running on Borg, and so there's a lot of things and moving pieces underneath it, and how do you know that they're reliable? We kind of made a decision here that we only allowed alerting rules to be set on in-memory data because of the dependency problem. We don't set alerts on the stuff that's stored in these systems because you can't depend on an emergency whether they're going to be there. There could be all sorts of things that could be breaking at the time. And we did something similar for Borgmon. We needed some extra way to make sure that your jobs are still running because Borg itself could be having problems. So what we did is we had several failure domains, and we had one set of Borgmons that we run in Podcast S3 called Metamon that goes out and watches everyone else's Borgmons just like it was another job. And we made sure that we ourselves are running because we have lots of these things running all over our production data centers that are all watching each other. So as long as one Borgmon instance is running in the company, we'll be able to know whether things are down and be notified about it. So some lessons learned. There's a lot to love about this system. It worked really well and enabled all sorts of monitoring that wasn't available before this. Some of the things, the composable, being able to customize your monitoring to a service was very flexible for service owners. The DSL was great. It was much better than what came before it, but that said, it was very crufty. And it had lots of sharp edges, lots of razor wire when trying to put together your monitoring configs. There's a famous story of a high-ranking engineer that spent an entire day trying to debug a problem with their monitoring, and it came down to the fact that within his config, A minus B was actually an identifier and not an expression. And once he found that, those sorts of problems are all over the place in DSLs if you're not careful. And so this ended up being kind of something we had to pay attention to. So let's move forward a little bit. Back in 2007, we're still growing at a crazy pace, and we're thinking more at this point of infrastructure as a product. Not necessarily as an end-user product, but a product for our own internal users. And so that changes our thinking a lot. We're doing more rigorous capacity planning. We're trying to look at SLAs and rethinking what we're doing and how we're doing it. So there were some major problems that were identified this time. TSPB, even though it's handling like very good and large volumes of data, the writing was on the wall. It copied all of its data to a central location and didn't really support having replicated data around. And it was already storing all of its data in the largest distributed storage cell that we had, the largest GFS cell that we had. And even if we wanted to replicate it somewhere else, it's not clear that as it grew, that we would be able to have enough capacity in other locations to be able to have a redundant copy of all this data. And really what you want to do is break it up and store a little bit in different places. Luckily, around that time, we had better tools. This is around the time that Bigtable came into a lot of usage at Google. And so instead of writing index files on disk, how about we use Bigtable? For the purpose of this discussion, you could treat it like a database, even though it has very different characteristics from your normal database. Instead, we still had something kind of like the indexer. Instead, we called it the collector. It went out and grabbed these log files from everywhere, wrote them to a Bigtable. And we did something clever in this case. We did some analysis about query logs and what people are looking at. And almost always, people are looking at the most recent data. It's mostly dashboards of what just happened. It's ad hoc queries when they're firefighting and want to figure out what the fuck just happened. It's all stuff that is recent. So we took a very highly provisioned Bigtable instance that had different latency characteristics and was highly tuned for fast performance, and just put the most recent data in this table, and we called it the head table. And then as data expired and then went off, we would have a process called the mover that would take this data, downsample it, and move it to something called the body tables. And these were separate tables that we could scale as big as we wanted. They could be stored wherever we wanted. And each table was responsible for a certain time range of monitoring data. So the hope was that this would allow us to grow to meet Google's future monitoring demand. So we called the system Dump Truck, and I love the name. It's shoveling data all over the place. It's fantastic. But oops, we were so focused on capacity and being able to store large volumes of data that we messed up with ingestion rates. And it turns out that as we grew, trying to shove all the data at the same time into one of these head Bigtables, even though Bigtable is massively scalable, it still had problems, and this ended up being a bottleneck. We quite frequently got backlogs in our ingestion pipeline. So we ended up having to shard the Bigtable, where we actually had multiple head tables, and a subset of the data would be stored in each table. And that allowed us to scale that arbitrarily to meet the demand, the ingestion demand. We also did a lot of thinking about monitoring as a service. Now that we were able to do these very complicated monitoring things, how do we make it easier? And in addition, the data model, like the label sets were great, but you could only do floating point values. How do we do more structured data types? And so there was a lot of things along those lines, and plus the vector-based data was a little bit tough to use, it was hard to reason about, and we wanted a better way of thinking about the data. And all these things result in a system that we call Monarch. It's targeted to a different set of users. It's targeted very much to microservices and small development teams that don't really have a lot of time to spend setting up their monitoring and tuning these special board one instances that they run themselves. It's a central service, and it was very ambitious. The goal of this was to be planet scale monitoring. We wanted to be able to have a central service that handled all of Google's monitoring data. And not only at the time, but to accommodate for future growth. And the data model was much more structured. It was something akin to a programming language. It supported all the data types that you have in modern programming languages. In addition to that, we had data types for map types, which are kind of like the label sets in BoardMon. We had distributions as a first class data type. And in addition to that, we had metadata. You could say that this metric was in bytes, and this metric was in kilobytes, and you could add them together and have a same result. Which is a very useful thing within monitoring systems. It had a general purpose query language. You can do general purpose computation on your data. We use a streaming protocol for doing that. We'll review these time series data as a stream of values over time and crunch the numbers as we go. Now, this stuff is still relatively new. But already we can talk about some of the lessons we've learned from trying to roll this out. The first one is that people were happy with BoardMon. it was a good monitoring system, so the table stakes were really high. And as a result, we have both systems in use, and we're not really pushing anybody off the old system, because if it works for you, great. But a lot of the newer projects that are coming along and smaller teams that are doing this, they are starting to use Monarch. But having that flexibility and be able to migrate from one system to the other is useful. So some other things I wanted to bring up. I noticed that there were a lot of other systems that are doing stream processing out there. And I don't know what problems that they run into. I can talk about some of the problems that we run into. You have to be very careful when doing stream processing, especially in a distributed system, because things go wrong. You might have a node in your evaluation tree that is not responding or is responding slowly, or maybe it's a query that has so much data that is overwhelming some particular node in your evaluation when you're streaming the data through. There's just too much data. I think they're calling it back pressure or buffering, or whatever way you use to handle that. It has a common problem. You have to be able to return an answer for that query. And then what do you return in this situation? Do you drop the data? Do you try and downsample the data? The one thing that I would caution about, and we learned from experience on this one within Monarch, is that no matter what you do, no matter how you handle it, make sure you return a repeatable result. Because what happened is we had users of our system that would run a query at a time where it was under extreme load and get an answer. And then 5 minutes later, they would run the same query again when it wasn't under load, and they would get an answer, but it would be different. And at this point, as a user of the system, what the fuck? Like, every time I run a query, I'm getting a different answer here. And from the user's perspective, you lose confidence in your system. And so a lot of thought is being put into making sure that the results are consistent, that we're able to answer these queries and handle these failure conditions gracefully. And anybody building a streaming system should do something similar and pay a lot of attention to this. So moving forward, it's now time to start talk about scale. Google's famous for scalability, and even scaling has limits. And around this time frame, scale really started to hurt within the company on all sorts of fronts. Now, how much scale are we talking about with monitoring systems? Here's some fun comparisons here. The New York Stock Exchange, at the height of the trading day, in raw tick data, is producing around 45 megabytes per second. That's a lot of data. But the monitoring systems we have, dump truck, we're on the order of gigabytes per second that is being ingested into our system. And as big as that is, Monarch is about twice the size of dump truck. Now, before we start thinking that we're hot shit and everything, then along comes CERN. These guys are crazy. These guys, when they're running CERN, they're generating a petabyte of data a second. Think about that. That's insane. I mean, they do a lot of downsampling. It's so much data that they have to do downsampling in hardware. But I mean, serious props to the CERN guys. It's an amazing system that they built there for handling this. But anyway, so we had to, so growth here was a big problem. We're dealing with lots of data, and you can't scale infinitely. Unbounded growth is not sustainable. And at the time, we started looking at this, our usage was growing 15% quarter over quarter. And so that is a tough capacity planning problem. And we did some analysis on that. We looked at our query logs and discovered that 99.9% of our data was collected and never ever looked at. That is incredibly wasteful, like ridiculously wasteful. Like, even if we could do it, why would you want to do that? So we had made a lot of changes to the service. Rather than logging everything to long-term storage by default, we turned it into a whitelist. And we also had a system that we put in bandwidth quotas to make sure that everybody had a limit and they had to stick to their limit for what they collected. And even more than that, we came up with a system for automatically blacklisting people based on their query logs. So if you weren't accessing the data but you're storing it anyway, we would do things behind the scenes. We would tell you about it, but they would also downsample the data and possibly not collect it at all. Monarch mostly avoided this problem because from the start it used retention policies. You had to tell Monarch what you wanted collected and what resolution you wanted it collected. And when it started storing persistent disk, you had all sorts of flexible options on a per metric basis to downsample in different ways and store it in longer time horizons. So now we're here today. We're here at Monitorama, and so what sort of things are we working on now? I've heard a lot of talking about pushing versus pull. It sounds like it's a religious debate. On our side, it's not religious, but for practical reasons, we're actually having to switch from a pull model to a push model. And I'm happy to talk about that on the chat channel. Some other things is we're doing all sorts of projects around zero config monitoring, trying to make sure it's easy as possible to onboard new services onto the monitoring platform. And also, there's a little thing called cloud. Google is trying to put together a monitoring product for its cloud offering. And I don't bring this up to shield the product or anything like that, but because it actually has a profound impact on our team. There's lots of things we need to do to be able to make this work. In particular, this is user data, and people can do all sorts of crazy things. I am sure at some point somebody is going to put a social security number in a metric, and we're going to have to be ready and be able to deal with that. So we're going around and throughout all of our monitoring systems adding encryption at rest. Any access to the data is restricted to a certain group of individuals and is audited. All access to this data is audited, and we have a record of it. And also, we had to pay close attention to scaling characteristics. We're so used to scaling with the amount of data and the volume of data we're collecting, but when you start making something like this available to the outside world, as many engineers as we have at Google, there are way more out there. So we need to be able to scale to handle many more configs and a faster rate of change to configuration within the system. And making sure that we're ready to meet that demand is an important part of what we're doing. So that's it. Thank you very much for having me today. I hope it was valuable.